Page 23, quality control charts. So I think it's safe to say we've got through the worst of this chapter, and what follows is pretty straightforward. Before I talk at you, I want to show you a quality control chart. Here's one example on page 24. This is what a quality control chart looks like, at least one of them. What you see here is a collection of data that's been plotted on a graph. Typically, one sample a day is called an individual's chart, or if you take multiple samples per day, you'd plot averages. Over time, these might be days here. You'll see a solid black line in the center representing the average, and then you see some hashed lines above and below representing so many standard deviations above and below the mean. Sounds like statistics, eh? So where are control charts used? Well, for example, incoming raw materials, the assay, its delivery time, errors in the orders, the process itself, the concentration of impurities, production rates, maintenance, repair time, corrosion or wear rate of tanks, marketing and sales, customer complaints, product delivery time. In the laboratory, concentration of secondary standards, recovery on spikes and standards. In fact, everywhere in the manufacturing and research industry, control charts are used. So you should be familiar with this. It will help you when you go to work. How to reduce variation. The fundamental point is that special cause and random cause of variation are treated differently. Recall Duran's rule. 85% of variation is random error in the system and can only be remedied by management making changes to the system. 15% of variation is special cause and fixable by the worker. So here are the steps in an SPC program. First of all, we identify the cause of variation in order to remedy it. And this is not always obvious. Often it is elusive because manufacturing operations are complex. There are many interrelated variables. Statistical control charts distinguish between common cause and special cause. That's a really important point to appreciate, and you will when we do the examples. They distinguish between common cause and special causes of variation. Step 2 is to remove the special causes. For example, we might recalibrate the instrument. We might store standards to minimize deterioration, etc. Once a process is free from special causes, it is said to be stable, even though it still has variation due to random causes. Step 3 is to estimate the process capability. It's a simple calculation, and I'll show you how to do that later. Step 4, establish and carry out a plan to monitor, improve, and assure the quality of the process. For example, charting, maintenance, training and record keeping, in order to constantly and forever reduce variation. That is the mantra of all the SPC gurus, constantly and forever reduce variation. The usefulness of control charting. It is very useful. It detects special causes of variation. It measures and monitors the common causes of variation. It tells the worker when to look for problems and adjust, and when to keep your hands off. It also tells us when we need to make fundamental changes. Page 24, Shewart charts. If a chemical process or laboratory is to generate high-quality product or analytical results, it must perform consistently from day to day and find a way to distinguish between random variation and special cause process problems. Shewart charts reveal time-dependent trends. We will consider two of the most important kinds, mean charts and range charts. So you're looking at a mean chart. Here you see days. This could be 25 consecutive days, or it could be 25 consecutive samples. We'll assume it's days for the purpose of this case. On the y-axis you have concentrations. We're measuring the concentration of milligram in a sample 25 days in a row. You'll see the blue line, joined by black dots, is the daily result for the magnesium value. And then we see some solid lines and hashed lines going across. Here's the data that's being plotted on the chart. So a mean chart may be constructed with one result per day. That's called an individuals X sub I chart. That's what we're plotting here. Or the average of several results per day, and that's called an X bar chart. We will consider the individuals chart first. So samples are analyzed over a period of time. In this example, we have 25 days, one sample per day. When 20 to 25 samples have been gathered, you calculate the average X bar and the standard deviation. On suitable graph paper, such as Excel, or at work we used to use pre-designed SPC charts, you construct a chart with the y-axis as concentration and x-axis numbered sequentially. These are the sample numbers or dates. We draw horizontal lines across the chart as follows. The black solid line at y is equal to x bar, or the mean. That's the center line, x bar. A red dashed line at y equals x bar plus 3 standard deviations. Here it is up here. This is called the upper control limit. A red dashed line at x bar minus 3 standard deviations. Here it is here. That's called the lower control limit. After calculating upper and lower control limits, x bar plus or minus 3 standard deviations, see if any of your points exceed these limits. These points should not be included in constructing the chart limits because these points are due to special causes. They're not common and they will skew the chart. So discard these out of control points and calculate new values for x bar, standard deviation, upper and lower control limits. This is not cheating. In fact, it would be cheating if you included these out of control points. Again, check the data to ensure that all the data lies within the upper and lower control limits. If not, repeat the process of discarding and recalculating data until all the points fall within the upper and lower control limits. Well, then you ask, what if I repeatedly cannot draw a control chart with all data within the limits? Well, that indicates that the process is out of control, it's plagued with special causes of variation, and you cannot use a control chart until you eliminate the special causes. This is a bad situation. Remember that only 3 results per 1,000 should lie beyond the control limits. So that is 99.7% of all data lies within plus or minus 3 standard deviations of the mean, if random variation is the cause. And such a process or data set is said to be in control. If data exceeds the limits more frequently than this is due to special causes of variation, and the process is said to be out of control. It's common practice to draw 2 additional lines on the control chart. Page 25. A dashed line at y is equal to x bar plus 2 standard deviations. This is called the upper warning limit. And a dashed line at y is equal to x bar minus 2 standard deviations. This is called the lower warning limit. Let's take a look at those. So here the blue dashed line is x bar plus 2 standard deviations. That's the upper warning limit. And the lower dashed blue line is x bar minus 2 standard deviations. That's the lower warning limit. So remember that only 5 results per 100 should lie beyond the warning limits. That is, about 95% of all the data lies within x bar plus or minus 2 standard deviations, if random variation is the cause. If you remember your normal distribution, the probability of 1 point alone falling between 2 sigma and 3 sigma, it's 2.5%. P is 0.025, and this is no cause for alarm. But the probability of 2 successive points falling in the same region is remote. It's 0.025 squared, or 306. That's like 0.06% or 0.6 in 1,000. If this occurs, the process is judged to be out of control. Investigation and corrective action are taken immediately. Okay, so using and interpreting individuals charts. Continue to plot new data on the chart in real time as the data is measured and collected. You circle any points that are out of control. These are out of the limits. Any out of control point should be immediately suspect for special causes of variation, and investigation is undertaken. There are some other checks for special causes. If you find that 7 or more consecutive points are on the same side of the mean, or 7 or more consecutive points are rising or falling consistently. This is all based on stats. For example, the probability of 7 successive points falling on the same side of the mean is 0.5 to the 7th power, or 0.008, or 0.8%. It's less than 1%, or less than 1 in 100. Periodically calculate X bar and standard deviation for a new set of data, minimum 25 points. If it differs from the values first calculated, you draw new lines for X bar, upper and lower control limits from that point forward. So that's an individual's chart, 1 point per day. X bar charts, when standards or samples are analyzed in replicate, duplicate, triplicate, etc., for each time period, for each day or for each shift, then we construct what's called an X bar chart. This is the same as the individual's chart, except that each point, X bar individual, that's plotted on the chart is the average of several data points. It's called a subgroup. So 1 point per period is a subgroup size of 1. This generates an individual's chart. 2 points per period is a subgroup size of 2. 3 points per period is a subgroup size of 3, and so on. X double bar is the average of all the subgroup averages. So it's equal to the sum of your daily averages divided by the number of subgroups, or number of days. But note here that the upper and lower control limit for an X bar chart are calculated as X bar plus or minus 3s over root of n, where s is the standard deviation of all the data. Note that now the control limits will be calculating using plus or minus 3s over root of n, not just plus or minus 3s, because means, not individual values, are plotted. Do you recall that s over root of n is a standard error of the mean, not just the sample, whereas s was a standard deviation of individual samples. There's a simpler method for constructing individuals and X bar charts, and we'll look at that a little bit later. Page 26, range charts, called R charts. If a Shewart chart for means, that's the X chart, suggests that a process is out of control, there's 2 possible reasons. The most obvious is that the mean has changed. If the mean changed, then your points can be out of control. An alternative explanation is that the process mean has remained unchanged, but the variation or range of the process has increased. The process is yo-yoing, making the control limits too tight. Hence, there is a need for a chart to evaluate the range of a process as well as its mean. The range is the difference between the highest and lowest data points in a group. If it's an individual's chart, it's the difference between 2 consecutive days. If there's multiple points in the same day, then it's the highest minus the lowest within the subgroup that day. Whereas X charts evaluate how close the process values are to some mean, a range Shewart chart evaluates the process consistency, the amount of deviation between samples or within a group. So for a process to be in control, its mean has to be close to some target value, and it must demonstrate a small range or variation. Control charts are constructed with the range chart directly below the individuals or X bar chart. So take a look here. Notice how the range chart, which is in blue, is right below the means chart in green. And the idea is that you line up the days. So if I want to look on a certain day, and I notice that there's a problem, say on day 11, then I want to look down at the range chart at the same time to see what's going on. So don't put them side by side, but make sure they're plotted one below the other. When more than one data point per day is analyzed and the daily average values are plotted on an X-bar chart, the range is to be the difference between the highest and lowest individual value of that subgroup that day. But if only 1 point per period or per day is plotted on the individual's chart, then a moving range can be plotted on a moving range chart. So the moving range is the absolute value of the difference between two consecutive individual values. We don't want negative differences. We're looking at magnitudes, so it's the absolute value of two consecutive daily values, say between today's reading and yesterday's reading. And thus moving range charts will have one less point than the corresponding individual's chart. So here on day 1 we have our first reading on our means chart, but there's no point on day 1 on the range chart. We can only get our first data point on the range chart when we get to day 2 because we need the differences. Page 27. So how do you construct an R chart? We'll calculate the average of the ranges, much the same as you did for the average of the means. R bar is equal to the sum of your range values divided by the number of range values. This will be plotted as a black solid horizontal line that'll be somewhere near the center of your chart. The upper control limit on the range is calculated as R bar plus 3 sigma, or using a formula derived from the normal distribution. The formula is D4 times R bar. You know what R bar is. And D4 is a factor obtained from tables that are used in constructing control charts. And the upper control limit on the range is drawn as a red dashed line on the R charts. Take a look. So here is the daily range values, and this black horizontal line is the average of the ranges. We have the upper control limit on the range chart as a red dashed line, and we have the upper warning limit on the range chart as a dashed blue line. The lower control limit is not often used on range charts, particularly when n is less than 7. So we'd use 0. The 0 line serves as the lower control limit. One of the reasons is that you'll often find the lower control limit calculates to a negative value, and that has no meaning. The upper warning limit is also commonly added as a dotted line and is calculated as D3 times R bar. It's not always the practice to plot the lower control limit and lower warning limits on a range chart, as a reduction in range is not normally considered to be a cause for concern. However, the variability of a process is one measure of its quality, and a reduction in range represents an improvement in the process. So if this is ignored, any real changes in X bar might go undetected. In addition, recognition of range reduction can be useful in finding sources of improvement of process stability. So you see, it's optional. Sometimes lower control limits on the range and lower warning limits are plotted, but you would not plot them if they calculate to be a negative value. Range charts can be used when no X individuals or X bar charts can be constructed. When would this happen? When standards are unavailable or too unstable to retain and analyze repeatedly. So what do? Well, instead, the actual unknown samples are split and analyzed in replicate, and the range, the largest minus the smallest, that's the R value, and the upper control limit on the range are calculated and plotted on the R chart. Quite clever. Disadvantages of an R chart? Well, they don't detect bias. They don't detect special causes of variation. This is cancelled out when the difference between analysis is calculated. It leaves only the random causes of variation. The range chart shows the precision of the values. Let's take a look in Excel and see how that's done. Take a look at an Excel spreadsheet where I've created the X individuals chart and the R chart for the data we're looking at. So here we see in row 20 the days 1 through 25, This is the individual values, the magnesium concentration each day that's plotted on the X individuals chart. X bar, if you can see in the formula bar, it's the average of all your individual values in row 21. So it's row 21. And when you calculate it, add absolute references so that then you can drag this formula across to all the adjacent columns and it won't change the formula. If you leave relative references and you'll be calculating values that go beyond the chart, it'll get messed up. The X bar should be the same number all the way across the chart. The upper control limit, and you can see it here, the upper control limit is the average plus 3 standard deviations. Right, 133 in this case. So that's the average X bar from row 22, here it is 99, plus 3 times the standard deviations of the individual. So you need to get the standard deviation of all the individuals. You can calculate it at the right, or I did it in the column on the left just so it's easier to see. So here are the X values, and I have the average and the standard deviation. So this would be H22, X bar is 99, plus 3 times the standard deviation, which is 11.2, gives us the upper control limit. The lower control limit will be the average minus 3 times the standard deviation. Here in row 25 we have the moving range. I don't have a value for the first point, but I do have one for the second. It's the absolute value of the difference between 2 consecutive individual values in row 21. The R bar is the average of all your range values taken from row 25. And again, use absolute references so you can drag it across. It'll be constant. And this will be it on the range chart down here, this line. The upper control limit on the range can be calculated as R bar plus 3 standard deviations of the range. So in the column E, I have the range values listed. There's the standard deviation. So this would be the average range, R bar, which is 13, plus 3 times 9.8, gives me the upper control limit on the range. The upper warning limit will be X bar plus 2 standard deviations of the mean. The lower warning limit will be X bar minus 2 standard deviations of the mean. And the upper warning limit on the range will be R bar plus 2 standard deviations of the range. So that's what it looks like. I have on Blackboard, I have instructions from your computer class to tell you how to do this in Excel. I just showed you how you construct an X individuals and R chart using what's called the long method, where you calculate the standard deviations and work from there. You have to appreciate that many workers on the shop floor in industry aren't able to calculate standard deviation. They don't have Excel in front of them to do it, or they simply have never learned how to use standard deviation. And so there is an easier method, and in fact sometimes it's a better method, more accurate, that uses data from statistical tables. I'm going to show you that. So this is called the shortcut method or the factor method. So we've seen that the standard deviation, whether it's S or sigma, of the process is pretty crucial to establishing control and warning limits. And hence it is important that the calculation of sigma is based upon a substantial number of measurements in a stable process. If sigma is calculated from data that suffers from some drift, the value of sigma may be overestimated, and so limits cannot be properly calculated. So what's the solution? Well, take a large number of small samples, measure the range R for each, and determine R bar, the average range. This procedure ensures that only the inherent variability of the process is measured. Any drift in the mean values will be eliminated. And then the R value can be used along with values from statistical tables to calculate the process limits. That's all one needs to do, is measure the individual values and calculate the ranges. Most people can do that, even without much schooling. And again, this is used on shop floors everywhere throughout process. People with minimal schooling can do this. So I'm going to call sigma that we calculate from the range rather than the formula for standard deviation. We'll call it sigma star. So it'll be the average range divided by D2. D2 is read from a stats table. Then using sigma star, we can calculate everything from here. The control limits can be calculated as the average of the averages, x double bar, plus or minus 3 sigma star over root of n. Now, you can also use the formula x double bar plus a2 r bar. This is typically what's used on the shop floor. It gives exactly the same value as the calculation on the left, but it's easier to use. A2 is read from a table. The warning limits can be calculated as x double bar plus or minus 2 sigma star over root of n, or you can use x double bar plus or minus a1 r bar. And again, these give exactly the same number. You can get a1 from a table. For the R chart, the upper control limit on the range is D4 R bar. The lower control limit on the range is D3 R bar. The upper warning limit on the range chart is D2 R bar. The lower warning limit on the range chart is D1 R bar. So X double bar and R bar are the arithmetic averages that you calculate from the data sets, and all the factors D1, A1, A2, D1, D2, D3, D4, they are simply read from tables based on the subgroup size. Take a look at page 28. So here on page 28 is a table of control chart factors, and these are commonly used in industry. So the leftmost column is the subgroup size. If you're using individual values, you'd use n is equal to 1. If you have 5 samples per day, you'd use n is equal to 5 and get your factors from that row. So here are the factors A1, A2, D2, D1, D2, D3, D4 to calculate all of your limits on your charts. Well, there are some examples for you to do in the following pages. So on page 30, I have the data that was used to calculate the charts I just showed you. On page 31, I have the charts that we just looked at. On page 32, I have another set of data for phosphate readings, and I'm asking you to create an individual's X chart and a moving range chart for this. That's an assignment for you to do. I've given you a template for you to work with to put your data into on page 33. On page 34, another example for you to work on. This is iron content in anhydrous HF. Here's a set of values for a period of 20 days. So here I've given you the daily averages, and I'm telling you the subgroup size is 3. So you will be plotting an X bar and R chart this time. On page 35, another data set for sulfate analysis. The subgroup size is 5. And here I've completed most of it for you. Here's are the individual values on a given day. I calculated X bar and R for you, and I just leave it for you to do the last few. This is the kind of thing you'd get in a test, because I don't want you to spend all your time doing all these tedious calculations without Excel. Typically this is done on a calculator in the school, right? I'll have the solutions to all of these assignments posted on Blackboard. Page 29. I want to show you a variation of control charts. These are called zone charts. In a zone chart, and I have, by the way, I have 2, 4, 6 zone charts, mean zone charts on the left, and I have 6 range zone charts on the right. And in these charts, the region between X bar and 1 sigma is called zone C. So C is near the center. The region between 1 sigma and 2 sigma is called zone B. And the region between 2 sigma and 3 sigma is called zone A. There are some patterns here that definitely are out of control. On the upper right, we see one of the points is above the upper control limit. and to the right of it we see a point that's below the lower control limit. And the terminology for this is UCLM, upper control limit mean. And this is LCLM, lower control limit mean, means they exceed those points. Just below it here we have an example of a whole bunch of points that fall within zone C. And the rule is when you have 15 or more consecutive points falling in zone C, that's definitely out of control. That's not normal. Points should be falling outside of zone C. If not, your control limits are too widely spread. So this is called a MCM. MCM stands for mid-range clustering mean. So the points are clustering around the mid-range. The next one we're going to look at is LCM. It's a limit clustering mean involving 8 or more points in a row outside zone C. So if you have 8 or more points in a row that never fall in zone C, that's out of control. That's called a limit clustering mean. 8 or more consecutive points that do not fall in zone C. And the last case here is one we spoke of earlier, a trend up mean, 7 points in a row increasing, or a trend down mean, 7 points in a row decreasing, abbreviated TUM and TDM. Take a look. 7 points in a row increasing, that's not normal. They should be varying. TUM, trend up mean. 7 points in a row decreasing consecutively, trend down mean. So I'm going to ask you to learn those 6 terms. Here they are on the left. I think they're pretty self-explanatory once you've looked at them. Now, on the right-hand side, we have the same situations but applied to a range chart. So the terms are identical, just change the last letter from an M to an R for the range chart. Here we have an upper control limit range outlier. Here's a lower control limit outlier that exceeds the lower control limit. Here's the mid-range clustering range chart. Here's the limit clustering on a range zone chart. And then we have trend up on a range and trend down on a range. Page 36, Shewart charts for targets. Thus far, our means charts plotted the average and limit values based on the process values, x sub I, x bar. Sometimes it's more instructive to plot the average line as the process target instead of the process mean, x bar, and then to plot the limits relative to the target rather than relative to x bar. Limits based on x bar can be used when x bar is well within the customer's specification or tolerance, and monitoring the process is sufficient. Or if there's no customer specification. For example, an environmental study might wish to monitor the hardness levels in groundwater. Clearly there's no target, it is what it is, we just want to see the range of results. Limits based on a target make sense when trying to keep a process on target with a specification. For example, 42.0% by volume calcium chloride is a target specification for calcium chloride solution used in road construction. Another common example is daily monitoring of the assay of an internal quality standard, IQC, in a laboratory to assess an analytical method's performance. In such cases, it's preferable to draw the center line as the target rather than the process mean. Here's a worked example. An IQC standard with a concentration of 50.0 ppm caffeine is analyzed in a lab 4 times daily for 25 days, and here are the results. The leftmost column has the day number, and the next 4 green columns are 4 results per day. The blue column is the average of the day, and the range is in the orange column on the end. So at the bottom here, we have the population standard deviation of all the data points is 2.43. We have the R bar, which is the average of all the daily ranges. and we have the population mean is 51.3. Recall the target for the IQC is 50. So the standard deviation of all the values is 2.43. If you calculate the population standard deviation based on sigma prime, r bar over d2, here's r bar divided by a factor from the table, you get 2.09. And 2.09, the population standard deviation calculated from the factor, is less than the actual population standard deviation calculated from the data. Okay, so since sigma prime is less than the population standard deviation, this suggests that the data is out of control. So limits really should be calculated using sigma prime, not from the standard deviation. Here on page 37 is the data plotted. We have the 50 ppm caffeine IQC standard. This chart plots X bar, that's what this blue jagged line is, but the center line is actually the target. It's not X bar, and the limits are calculated based on the target, not based on X bar. The target is 50, not 51.3, which is X double bar. At the bottom here, the range chart is also shown. The range chart appears to be in control, but the means chart shows evidence of drifting. In addition to 5 out of control points, 1, 2, 3, 4, 5, on the means chart, samples from day 3 to 15, from here all the way to here, are above the target, followed by a downward drift till day 21, and then an upward shift again. Clearly this process is not in control, and this is a good example of why sigma prime, calculated from factors 2.09, should be used instead of sigma from the standard deviation of the data. If the data is not normally distributed, if it's out of control, it will bias or skew your results. Page 38, Qsum charts. The average number of measurements necessary to detect a significant change in the process, mean, is called the average run length, ARL. The ARL on Shewart charts can be quite long. However, it is unacceptable to run a process in an out-of-control condition for many days before a problem is detected. Qsum charts increase the speed with which a control chart detects that a change in the process has occurred. A Qsum chart, that is a cumulative sum chart, is shown for the data below. The target result is 80. So here we have 15 days worth of data, a single result on each day. The target is 80. In the third column, the difference of each day's result from the target is calculated. So on day 1 we have 82 minus 80, the difference is 2. On day 2 we have 79 minus 80, negative 1. 80 minus 80 on day 3 is 0. 78 minus 80 on day 4 is minus 2, and so on. In the fourth column, the Qsum column, the differences of column 3 are simply accumulated. So here we have 2 plus 0, well that's 2. 2 plus negative 1 is plus 1. 1 plus 0 is 1. 1 minus 2 is negative 1. Negative 1 plus 2 is 1, and so on. If a process is on target, then the cumulative sum of its deviations from the target should be 0. If, however, a process drifts from its target, the cumulative sum of the deviations will move away from the target. And this is the concept that Qsum charts use to detect change. On the next page, the daily results are plotted on an X individuals chart, and the cumulative sums, Qsums, are plotted on a Qsum chart for comparison. Sigma prime is used to establish the control limits rather than standard deviation of the data, because the data is not known to be in control. The upper and lower control limit values on Qsum charts are often drawn at plus or minus 4 sigma and occasionally at plus or minus 5 sigma, depending on how tightly the process is to be controlled. So the upper chart is the individual's chart. The average is the target. We're plotting 80 rather than the actual average. The upper and lower control limits on the individual's chart are plotted using, don't know if you can see this, we calculate sigma prime as r bar over d2. It's 1.58. d2 is the factor from the table. And so our upper control limit on the individual's chart will be the target plus A2R bar, 84.8. The lower control limit on the individual's chart will be T, target minus A2R bar, 75.2, done in the standard fashion. Take a look at the Qsum chart. The upper control limit is 4 sigma. And recall, sigma is calculated as r bar over d2. Lower control limit is minus 4 sigma. In the upper individual's chart, an out of control point is identified at day 15, way down here, when it finally falls outside the lower control limit. In the lower Qsum chart, down here, an out of control condition is identified after day 11, when the Qsum value falls below the lower control limit. The Qsum chart identified the out-of-control condition 4 days sooner than the individual's chart. On the Qsum chart, the sum line initially varies close to the target, y is equal to 0, but the process steadily drifts from the target after day 8. So Qsum charts are very useful for early detection of out-of-control conditions. Page 40, process capability, is the ability to consistently meet or exceed specifications. So a process is said to be capable of high quality when 4 things are true. Number 1, the location or center or average of the measurements is on target. In this diagram, the center line would represent the target. Number 2, the spread or range of the measurements is narrow. It should fall within the specification. So on the left here we have the lower spec limit. On the right we have the upper spec limit. Our distribution should stay within that. Number 3, the shape of the distribution is normal. If the shape of the distribution is skewed left to right, it would suggest that special cause variation is present. And number 4, all 4 of these should remain constant over time. The process must be stable or in control. So if you look at condition C, it's certainly not stable. The average is moving, and furthermore the spread is too wide. It falls beyond the specification limits. Condition B, we can say the process is in statistical control. It's stable, and the distribution is normal. However, the spread is still too wide. This process is not capable. Process A is, of course, the best. It's stable over time. It's capable. It falls within the specification limits. The distributions are normal. Take a look at the next illustration. On the left side, we see 2 processes that are stable. Notice how the mean is not changing over time. It's stable. On the right side, we have processes that are unstable. The mean is changing. Look along the top row. These processes are not capable. The spread is well beyond the specification limits, and furthermore, in this case, the distribution is not normal. Special causes are likely at work. This one's all over the place. On the bottom row, we have processes that are capable. The spread of the product, the variation of the product, falls well within the specification limits, so they're capable. However, on the bottom right, this is not stable. Only the bottom left is capable and stable. It's in control. Page 41, process capability or capability index. Process capability, CP, is simply the ability of a process to meet a customer's product specification. assuming the process is centered on target. The process must be in control, random variation only, before Cp can be calculated. How do you calculate Cp? It's the customer's tolerance divided by manufacturing ability. What's the tolerance? Well, the tolerance is the range of specification. It's the upper specification limit minus the lower, U minus L. What's the manufacturing ability? Well, that's the process variability, and that's generally considered to be 6 sigma. So U minus L over 6 sigma. Simple calculation. Recall that 6 sigma is the range of concentration which includes 99.7% of all the previous product that's been shipped. This is an interesting chart. So plus or minus 3 sigma, that's 6 sigma, 99.7% of all the product falls in that range. If we go to plus or minus 4 sigma, that's 8 sigma in total, 99.9937% of product falls in the range. If we go to plus or minus 5 sigma, in other words 10 sigma, that includes 99.999943% of all results or product shipments. And if we go to plus or minus 6 sigma, it's getting astronomical. 99.9999998% of all values would fall within the range of X bar plus or minus 6 sigma. Try this exercise. A customer's specification for hydrofluoric acid is 70.0 to 72.0% HF. Previous product shipments averaged 71.0% with a standard deviation of 0.25. 5 is deprecated. Calculate the process capability for meeting the customer's specification. Well, let's do that. So process capability, Cp, is equal to the upper specification limit minus the lower specification limit divided by 6 times the process standard deviation, 6 sigma. Okay, so we're given the upper spec limit, 72.0%, minus the lower 70.0%, divided by 6 times the population standard deviation, 0.25. So that's 2.0% divided by 6 times 0.25 is 1.5. The value is 1.33. Units are not generally reported. It's a dimensionless value. When process capability is equal to 1, it means the supplier can meet the customer's specifications 99.7% of the time. That sounds pretty good, right? If Cp is less than 1, then the supplier can produce off-spec material more than 0.3% of the time. If Cp is greater than 1.33, then the process can demonstrate 99.999% conformance to customer specifications. North American automakers generally require that their suppliers maintain a Cp of greater than or equal to 1.33. Wow, pretty tight. Capability ratio is another term for Cp. CR, capability ratio, is simply the inverse of process capability. For example, a Cp of 1.33 is equivalent to a CR of 1 over 1.33 or 0.75. So a capability ratio of 0.75 means that the process spread occupies 75% of the tolerance. Obviously, the lower the capability ratio, the more capable is the process. Page 42, Cpu, Cpl, and Cpk. Take a look at this illustration in the lower left corner. Recall that Cp was the ratio of the length of the tolerance, upper specification limit minus lower specification, divided by the spread of the process, which is generally taken to be 6 sigma. You can see by the length of the lines here that the ratio is about 2 to 1, and so our Cp is in fact 2, and that's good. But look what happens when the process moves off target. The ratio of the tolerance to the process spread hasn't changed. The Cp is still 2, but obviously you're going to get some product possibly out of spec on the high side. In this case down here, again, the tolerance hasn't changed, nor has the process spread, but certainly we're going to produce about half of our product off spec on the high side, not much on the low side. You can see that as the process mean changes, Cp really doesn't give us a complete picture of the process capability. So we need some other indicators. Up here we have CPU is the upper process capability. It's the process capability to meet the upper specification limit. And Cpl is the lower process capability, the process capability to meet the lower specification limit. Here's the formula for CPU. It's the upper spec minus the process mean over half the spread of the distribution, 3 sigma. Likewise, Cpl is x bar, the process mean, minus the lower spec limit, divided by 3 sigma. Let's look at this in our examples here. CPU is equal to the upper spec limit minus x bar, process mean, divided by 3 sigma. And Cpl is equal to the process mean minus the lower spec limit over 3 sigma. So in the first case, the upper spec limit minus the process mean divided by half the process spread, 3 sigma. You can see that's about 2 to 1. So here's Cp upper is 2 to 1. Let's look at Cpl. X bar, the process mean, minus the lower spec limit, that length, divided by 3 sigma. Again, that's about a ratio of 2 to 1. Cpl is equal to 2. Take a look at the next one. Upper spec limit, which is here, minus the process mean, divided by 3 sigma. Well, they're the same length. So Cpu is going to be 1 in this case. What about Cpl? Well, Cpl is the process mean minus the lower spec limit divided by half the process spread, or 3 sigma. That's 1, 2, 3. So x bar minus L is about 3 times as long as half the process spread. That looks like the Cpl will be 3. So it's going to be good at the low end. It's unlikely that one would produce off-spec product on the low side. How about this case? Upper specification limit minus the process mean, well, they're equal, so it's going to be 0 divided by 3 sigma. In this case, Cpu is actually 0. It doesn't sound very good. And take a look at it. This indicates that 50% of the time your product will be off spec on the high side. How about Cpl? Okay, so we have x bar minus the lower spec limit divided by 3 sigma, half the spread. 1, 2, 3, 4. So the tolerance is 4 times longer than half the spread. So Cpl is 4. Almost never going to get material product off spec on the low side. One more case. The upper spec limit minus the process mean, but the process mean is actually larger than the upper spec limit divided by 3 sigma. They're the same length, but this is going to be -1. So here I've got CPU is equal to -1. That looks really bad. Pretty much says that 100% of the time the product will be off spec on the high side. How about CPL? Well, CPL is the process mean minus the lower spec limit divided by half the spread. That's 1, 2, 3, 4, 5. So that's a ratio of about 5 to 1. So there's CPU and CPL. Obviously, the higher the values, the better it is at achieving on-spec product at the low side or at the high side. So what's CPK? Well, CPK, notice, is the lower of the two values. CPK is 1 here and CPU is 1. CPK is 0 because CPU is 0. CPK is the lower of CPU or CPL for a given situation. CPU is -1, so CPK is -1. All right, so that's a better measure of how capable a process is. Page 43. Let's do this exercise. In the graph below, mu is the process mean, and T is the customer's specification target. The units on the graph are milligrams per liter. The standard deviation of the distribution is 2/3. Okay, so let's try these calculations. Cp is equal to the upper specification limit minus the lower specification divided by 6 sigma. Okay, so that's upper spec minus lower spec, this whole distance here from 18 down to 10 divided by 6 sigma. That's equals to 18 minus 10 over 6 times 2/3. So that's 8 divided by 4 is 2.0. That's a pretty high process capability. All right, let's try the next one. CPU is the upper spec limit minus the process mean divided by 3 sigma. So here we'll have it's U minus X bar, or mu in this case, divided by half the process spread, 3 sigma. It's going to be 18 minus 13 divided by 3 standard deviations, 2/3. That'll be then 5 over 2 is 2.5. So it's really good. The upper process capability is really high, and that's because our process has shifted to the low side of the target. But what's the lower process capability? Well, that would be the distance from the mean to the lower spec limit divided by 3 sigma. So that'll be X bar minus the lower spec over 3 sigma, half the spread. X bar was at 13 minus the lower spec is 10 divided by 2 from the previous calculation. 3 over 2 is 1.5. So our lower process capability, CPL, is significantly less than the upper process capability. So CPK is the lower of the two. So we're going to have to report 1.5. Do you recall what the capability ratio was? It's simply 1 over Cp. So 1 over 2 will be 0.5. One-sided specifications are common in chemical industry, where a customer specification is a maximum impurity. They might guarantee that the arsenic is less than or equal to 25 ppm, or you could say not greater than 25 ppm. Sometimes we see minimum assays. The minimum assay on commercial 50% NaOH is the spec is greater than or equal to 50% value. CPU is used where you have to ensure that you're not exceeding a maximum, and CPL would be used where you have to ensure you're not below a minimum value. Try these. Arsenic determinations on past shipments averaged 19.0 ppm with a process standard deviation of 2.0. The customer's specification is 25 ppm max. Calculate the process capability of meeting the specification. So that's an upper limit we're looking at. So we're going to use CPU is the upper specification limit minus the process average divided by 3 sigma. The upper spec on this is 25 ppm. The average is 19.0 and the standard deviation on that is 2. So we have 6 over 6 or 1, so the CPU is exactly 1. Let's try the next one. Sodium hydroxide assay of past shipments averaged 51.0% with a standard deviation of 0.50. The customer's specification is 50.0% minimum. Calculate the capability of the process in meeting the specification. This is a lower spec limit, so we're going to calculate Cpl, which would be X bar minus the lower spec limit over 3 sigma. The average we're told is 51.0 minus the minimum specification of 50.0 divided by 3 times the standard deviation of 0.5. So that's 1 over 1.5, 0.67. So that's not excellent. Page 44, suggestions for what should be charted. Chart the concentration of key reagents, particularly those that are used to certify product shipments. For example, secondary standards like 1 normal NaOH for acidometric titrations. We did this a lot at work. Normality is routinely checked against the primary standard like KHP. Any normality changes in the stock reagent are posted and causes for change are investigated. Might be a different analyst, different technique, deterioration of the reagent. Sodium hydroxide does absorb CO2. So if you nitrogen pad the reagent, you eliminate CO2. Known standards are run with every batch of sample. That's normal event, but have you ever thought about maybe plotting the absorbance of a given standard on a weekly basis? So a change in the absorbance might give information about the behavior of the instrument. Chart the analysis of a finished product. That's important. That will allow you to determine the CP or CPK for your process. Customers definitely want this information. Now you must decide which parameter to plot, because a typical certification of a shipment might have 8 or 10 different parameters or specifications. You probably wouldn't have time to plot all the parameters. So we discuss with customers, management, and workers which parameters are critical. Concentration of the main component and certain impurities. For chemical process operators, there are many important parameters like temperature and flow and pressure, and most reactors and vessels have gauges that continuously output electrical signals that come into the central computer that's used to control the process, and these are automatically charted. By monitoring the process, not just the product quality, control is achieved by prevention rather than detection. Operators can distinguish between common cause and special cause of variation. If it's a special cause, they can begin to investigate and adjust the process. In response to random variation, an operator will know when to just allow the system to fluctuate naturally. It avoids a common operation error called over-controlling. So who decides and who does the charting? Well, ultimately, that's management's responsibility, but typically a company will often establish a quality team that would include key members such as the internal quality assurance officer, perhaps an SPC specialist, a process engineer, a lab foreman, a process operator, maintenance foreman, And this group will usually make key decisions as to what's being charted. They would meet weekly or perhaps at a minimum monthly. The team would then make decisions as to what to recommend to management for improvement. Are there any benefits to control charting? Absolutely. It's often found that control charting gives operators better process control, also increased accountability to management, good or bad, greater pride in his or her work. It gives credibility to the operator's recommendations to management regarding the need for repairs or improvement or replacement. Furthermore, many industries must be able to demonstrate process capability if they're going to win and keep customer contracts. The ISO and QS standards, they've gained worldwide recognition in recent years, and as a result, many companies have invested considerable resources towards QC, QA training, quality specialist positions, and equipment. On page 45 and following, there's a discussion of some additional tools used for quality, flow charts, cause and effect diagrams, check sheets, Pareto charts, and such. This I'm going to leave you to read. There's no worked examples or calculations for it. It's pretty straightforward. So do your best with it, and that'll be it for the chapter on SPC.